Welcome back, and also welcome back to people online. So after this first step, we're going to take the second step in studying change. So the floor to Marleen.
Yes, thank you. So I hope you had a good coffee break and taken in some new energy to survive the second part. Well, now that you already heard me talking in the first part, you're kind of familiar with my style. So I think you will hear more of the same, but then we will talk about different types of models. And we take about 1 hour for my presentation. I hope that fits. Then we are going to switch to the tutorial part, working in R on some scripting and running some models yourself. We'll see how that goes. So we'll probably have a 5-minute little break in between. So you can quickly go to the toilet if you want to, or have a short break. And then we prepare for the tutorial parts, which also takes about an hour. Okay. Yes, so this talk is about studying change. Is it real or not? And typically we don't think about that. We're just going to study change. And if we see changes in means, we think, oh, there is change, right? But is that real or not? That's what we are going to talk about. And the formal models that we are going to talk about today are called longitudinal measurement invariance models. So we are going to test whether the change we see is really a change in the underlying constructs that we are interested in, or whether there's some measurement bias, whether there's a lack of measurement invariance in the instruments that we use to assess the latent construct. That's what it's all about in a nutshell. So let's first have a look at some questions that we might have when we are interested in change. Then I'm going to introduce the whole principle of testing for longitudinal measurement invariance to you. We are going to discuss some issues that are still out there when testing for measurement invariance. A lot, we know how to do it already, but there are still some methodological issues that people are working on. And then we'll arrive at some conclusions, and I will also suggest some further reading to you and some further practice. And that's what we are going to do in the hour after that. I have prepared an assignment for you in using R, Lavan, the same kind of scripting that we already saw a little bit in the previous presentation. And you will hopefully get some practice on how to run these kinds of models and how to look at the output and draw conclusions about the type of change that we see. Is it real or not, so to say? Okay, when studying change, well, what are the kind of questions that we are often interested in our field, psychology or beyond? Well, again, thinking about longitudinal cohort studies, many of you are involved in such studies. You might be interested in questions about change and development. For example, you would like to know, how does child IQ develop across time? Or how does parenting competence change across time as a function of gaining more experience as a parent? How does this parenting competence change across time? And also in randomized controlled trials, we're often interested in change, right? So for example, we want to evaluate the effect of psychotherapy on change in depressive symptoms. We hope it works. We hope it leads to a change, a decrease in depressive symptoms if the therapy works. So we're also interested in change. And another study that I was involved in myself, studying fathering, was about the effect of nasal oxytocin administration on fathers' involvement with their children. So if we give them hormones externally distributed, does that impact the way they parent or the way they are involved with their children? It's also a question about change. Does it make them more involved? So here are two examples with regard to what was found when studying change. This is from our own cohort study, or actually I should say Carlo's cohort study that I used to be involved in, and Miriam Oosterman's study, the Generation Squared study, and parenting self-efficacy, which I sometimes equate to competence. We can debate about that, but here I mean perceived competence as a parent. So this was studied in this cohort, both during pregnancy, so the expectations of a parent's ability to parent, how do they think they will do, and after giving birth to their child, they were followed longitudinally. Here 3 measurements were taken into account. And what you see in these studies with regard to parenting self-efficacy, that there seems to be an increase across time. Well, we can question, well, is that a real change? Or is it really true that parenting self-efficacy changes across time? Or perhaps because mothers become a parent and they gain experience as a parent, maybe the way they interpret the questions assessing parenting self-efficacy might change. And then there's a measurement difference rather than a true difference in parenting self-efficacy. So the means cannot be directly compared. So that's the question we are going to ask today, and we are going to see which models can we use to address that question. And also in the context of randomized controlled trials, you have also this interest in change. So for example, this is quite an old study where they looked at it was a randomized controlled trial comparing different psychotherapy groups and also control group and looking at change in depressive symptoms before the therapy and after, so pre-test and post-test measurements. And in this study, there are many studies out there studying the effect of psychotherapy on depression, but this is one of them that I highlighted. They found indeed a decrease in depressive symptoms, but a similar decrease across all groups. So also in the control condition, they saw this decrease in depressive symptoms. So it could not be attributed to the psychotherapy. But they did observe a decrease. And again, we can ask ourselves, is this a true decrease? Did these people really become less depressed? Or perhaps because they did therapy, maybe it was a group session, maybe they discussed about their depression, they became more aware of symptoms, or they started comparing themselves to other people with depression, and they thought, well, I have this, it's not that bad, maybe I'm not that depressed, and the other person is much more depressed. So this might change the way you think about depression and also answer the questionnaires that assess depressive symptoms. So is it a real change that we observe here, or is there a change in measurement? So with regard to measurements, well, you can sometimes directly observe behaviors, and sometimes that's not the case. And in fact, for many of the things we study, psychological attributes, psychological variables, like depression or like parenting self-efficacy, that's something that's in your head. You could say you cannot directly see how what is the level of parenting self-efficacy when you see a parent, and it's also not directly visible when I just look at you. Well, what is your level of depressive symptoms? There's no way of knowing this. So I cannot directly observe the constructs that I'm interested in. So psychological constructs, they tend to be difficult to observe and also complex in nature. So what we need is a measurement model for that. And typically you will see something like this. This is a confirmatory factor model. You might be familiar with that. What we kind of assume is that there is a latent construct. It's not directly observable, but it does exist, like the extent to which you are depressed, depressive symptoms, your depressive symptoms level. And we assume that this latent variable has an impact on how I answer questions that are indications of depression. So like, for example, my mood, or whether I socially withdraw, or whether I often feel guilty, or whether I have a loss of appetite. This is a somatic symptom of depression. So those are indicators of the latent construct, and we can try to measure those indicators and link them to something that we cannot directly observe. And this is a way to indirectly try to get a hold on this, the level of depressive symptoms of the people I'm interested in. So for this, we use a measurement scale, an instrument, a questionnaire often, and we need a measurement model to link the indicators, to link what we observe, in this case, the answers to the questions on the questionnaire about depression. We need to link them to the underlying, not directly observable construct, which is depressive symptoms. And we need to think about the psychometric properties of this scale. We want to assess, make sure that these items assess depression and not anxiety or something else. And we also want to do this in a reliable way. We want to know whether the scores that we obtain are reliable or not. So that's basically what psychometrics or measurement in psychology is dealing with. Well, thinking about such measurement models, there can be shifts in the way you respond to these items, shifts, which is called response shifts. So, for example, thinking about depression in the context of a randomized controlled trial, we might have a pre-test measurement of depression. We measure the depressive levels beforehand, then we start the therapy, and afterwards we measure the depressive symptoms again with the same questionnaire, right? This is how it's typically being done. And then that means that we have this measurement model linking the items, the questions people answer about their mood and feeling guilty, etc. We link that to depressive symptoms at the pre-test measurement, but we have the same measurement model at the post-test measurement. And we kind of assume and hope that the same model applies, because if it doesn't, if at pre-test these items are indication of depression and at post-test these are indications of anxiety, then we are comparing apples with pears, right? So then something goes wrong. And it is an extreme case, of course, but this is basically the idea. So what could happen when there is a response shift is there's a change in the frame of reference. So the way you think about the question that you need to answer and the way you answer the question, there might be a shift in that, comparing a pre-test and a post-test measurement. And this can be the result of the intervention. Or it can just be a result of changes across development, thinking about parenting. The way you answer questions about parenting might change as you gain more experience as a parent, maybe with success experiences or failure experiences. And also maybe your child grows older, so new demands are asked from you as a parent. It makes difference whether you're raising a baby and when you're raising a toddler, you have new challenges probably. So this might change your frame of reference, and it might impact the way you answer the questions that try to assess parenting self-efficacy. Although maybe your parenting self-efficacy by itself didn't change. That could be the case, that the true levels remain the same, but the way you answer the questions has changed. And that would suggest a change in parenting self-efficacy, while in reality, there's no such change. And that's something we want to tease out, we want to get to know. So longitudinal measurement invariance models are models that try to investigate that. So is there indeed a change in the frame of reference, so to say? So think about a single item that is an indicator of depression, feeling guilty. This is from the Beck's depression inventory. So it is a real item to assess depression. It's being used in research. It has 4 answer categories. I don't feel particularly guilty. I feel guilty a good part of the time. I feel quite guilty most of the time, or I feel guilty all of the time. And what we try to do is link that indicator to the latent construct, the depressive symptoms. And you can imagine that at pre-test, well, maybe you have a high level of depressive symptoms. And when you are confronted with that question, you're very likely to answer 3. I feel guilty all the time. I feel really bad. I feel guilty all the time. I have these guilty thoughts just all the time. So you cross the 3, right? So the level of depressive symptoms, your true score of depression, impacts how you answer that question about feeling guilty. And what we typically say that there is some threshold. So when you are scoring beyond a particular threshold on your level of depressive symptoms, so you score really high beyond this threshold, the blue line, then we say, well, then you will answer with response option 3. You will say, I feel guilty all of the time. And if you feel less depressed, you will answer maybe a 0, a 1, or a 2. Now, suppose that this is the situation at pre-test. You have quite a high level of depressive symptoms and you cross the 3. You say, yeah, I feel guilty all of the time. But then you entered into psychotherapy. This was a group therapy. Maybe there was a psychoeducation component about depression. So what you learned about depression and yourself has changed as a result of the therapy. And also maybe you were able to compare yourself to others. And you noticed, well, yeah, I feel depressed, but not that depressed, not that I feel guilty as others. So at post-test, you are confronted with this question again. And maybe your frame of reference has shifted, has changed. And now suddenly, given the same level of depressive symptoms, suppose that your level of depression hasn't changed in reality. The true score remained the same. But because of this shift in frame of reference, even though you score high on the latent level, on the true level, you might now be less inclined to cross the 3. You say, yeah, well, I feel guilty most of the time, not all of the time, right? So in what we observe with regard to this item, and it could also happen to other items of the questionnaire, is that it suggests a change. It suggests that the depressive symptoms have decreased because first you felt guilty all of the time, and after the therapy, you felt guilty most of the time. So this, if we would use this for a sum score of depression, it would suggest a decrease in symptoms, right? But in reality, the depressive symptoms have remained the same. And it's just that you started to interpret this item in a different way because your frame of reference has changed. That is the issue of measurement variance. And if that happens, you would erroneously conclude that depressive symptoms have decreased, while in reality they remain the same. So you draw an incorrect conclusion about the effect of psychotherapy on depression, and that's something you, of course, don't want. So that's the issue of longitudinal measurement invariance, to be able to compare means across time and to talk about real change. If we see differences in means, we want to first establish that we measure the same underlying constructs, that our measurement instrument is measurement invariant across time. So we want to establish longitudinal measurement invariance. Now let's have a look at how this all works. How do we test for longitudinal measurement variance? And there we start with the modeling again. I used colors this time to help you out a little bit. I hope this helps and it's visible. So this is the confirmatory factor model that I already just talked about. This is the measurement model linking the observed behaviors, typically items on a questionnaire, with what we are truly interested in, our psychological construct, which is our latent variable. So we have observed variables, typically items. In blue, we use squares for that to say that this is what we observed. And we hope we can link it to this latent variable, our psychological construct of interest, which we denote with a circle. I've now made it green. And we also call it, instead of a latent variable, a factor. So the abbreviation of F stands for factor and V stands for variable. So in this example, we have 4 items that we think are good indications of some underlying latent variable. Well, then we see other circles in purple. Those are the residuals again, residual factors, we can call them. So those are those factors capture everything that we didn't directly observe because we didn't measure it, that is unrelated to our latent variable. So it's not depression, but there may be other influences that impact how I answer the question about feeling guilty, for example. Can be just measurement in error. Maybe I'm just not keeping my attention where I'm filling in the questionnaire. It leads to some error in the answers, but it can also be other influences like age, or maybe I also measure a little bit of anxiety symptoms in there. That is all captured by those residual factors. So all variance in the observed variables that are not attributable to the latent constructs that I'm interested in, but represent something else. Then so these are the variables, latent and observed. And now we also have all kinds of paths with either numbers or stars already connected to them. Let's first have a look at the black lines over here. Those are called factor loadings. So those link the latent variable with the observed variables. So, and the direction goes from the latent variable because we assume that our underlying depression levels, our symptoms of depression that impact, that causally influence how I respond to this guilty item, right? And we can look at how strongly the observed variables are related to the latent variable. Is feeling guilty really a strong indicator, strongly connected to depression? Or is it weakly connected because it's not really a good indication of how depressed I feel? That's something you can infer from looking at the factor loadings. And then with regard to the residual factors, we can estimate, there they are again, residual variances. So how much error variance is there? How much variance is there left unexplained when we look at the variance of each of the items? And we also have the mean model. We also have intercepts. They are typically denoted by triangles. And we can estimate intercepts for each item. This is very briefly the confirmatory factor model. And that forms the basis of everything we do when we test for measurement invariance. Oh, and we have the factor mean as well. We can also estimate the factor mean and also its variance. I will come back to that. I don't want to get into too much detail, but maybe some of you will ask anyway, then we'll see. Otherwise, I won't bother you with that. So we can look at the regression equation, basically. And now the variables are not centered yet, so we have intercepts. I used a slightly different notation, just an intuitive notation, not a formal one with Greek letters. So, for example, variable 1, the response on item 1 is a function of the intercept of item 1, plus the factor loading times the score on the latent variable on the vector. So someone's true depressive symptoms score, plus some error term, some residual term. And we have the same for the responses of all individuals on the other items in the model, items 2 to 4. Well, we can translate these regression equations into expected variances and covariances. So what does this model imply in terms of how the variables are correlated with each other and what the variances are, how we can explain the variances of these observed variables. So for example, the variance of variable 1, the variance in that particular item, it can be the guilty item, is influenced by the factor loading, so the strength, how strongly this item is related to the latent variable, times the variance of factor 1, which is 1 in this specification, times the factor loading again. So it's the factor loading squared. That represents the extent to which variance in variable 1 is explained by variance at the latent depression level, plus variance in the residual factor. So the residual variance. So we decompose the variance of the item into a part that's being explained by depression. That's what we hope, that that part is large. And there's also some residual variance, external other influences, probably also impacting the responses on this variable. And we have the same type of specification for the other 3 items. And then we can also look at the expected covariances. Well, the covariance or the correlation between item 1 and item 2 is there. We expect it to be there because both items are indication of depression, right? So this would create an association between the items, among the items. And we can formally work that out. So for the covariance between variance 1 and variance 2, the model implies that this is given by the factor loading 1 times factor loading 2 in this model. And we also have the expected means, and that is important for now because we want, in the end, we want to compare means across time. And we want to know, can we really do that? Or is there a measurement problem? So the means model is also important here. In the cross-leg panel model, we kind of ignored it. But here we don't, it's really important. So the mean on variable 1 is a function of the factor loading of item 1 times the mean of the factor, which is here constrained to 0, plus the intercept belonging to item 1. So you are left with the intercept. Keep that in mind. It's a lot of formal stuff. Well, this model, if you test for measurement invariance across groups, you can use a multi-group confirmatory factor analysis. You can say, well, I have my depression questionnaire and in men and in women, and I would like to know, do men and women interpret these questions in a similar way? So does this measurement model, is it the same in men versus women? So then you would have this model, this measurement model, both in group 1, the men, and also in group 2, in the women. So this is a multi-group confirmatory factor analysis, and it's typically used for testing measurement invariance across different groups. But now that's not what we want, because we don't have different groups. No, we have different time points. And we want to compare this measurement model at pre-test with the measurement model at post-test, right? Or maybe we have even more longitudinal data in our cohort study. We have multiple waves, and we want to know, does this model hold at each wave? Do we measure the same thing at each wave or time points? So then we need a confirmatory factor model for repeated measures. So instead of having them as groups, just 2 different models, we have them now next to each other. It's visually more attractive to represent time. And we have the measurement model at time point 1, and we have the measurement model at time point 2. And then rather than having a multi-group confirmatory factor model, we need to specify the dependencies across the repeated measures, so to say, because these variables, depression can be related, true depression levels can be related across time, right? The pre-test level and the post-test level. So we are allowed for a correlation between the repeated measures, between the time points for the latent construct. That's the correlation you see really below on the slide. And then in addition, when we look at the residual factors, all the external influences that extend the way we respond to those items, they could also be correlated across time, right? Because if anxiety really also feeds into the way I answer the question, I feel guilty, then this external factor, which is anxiety, feeds in maybe to the items at both time points. So the residual factors are also allowed to be correlated. So that's why for each item, you see that the residual factor can correlate or co-vary with that same item on the other time point. Not across items. You could also do that, but that's typically not the way it's being modeled. This is kind of an assumption that all the cross-item correlations are being explained by the fact that they belong to the same latent construct, and not that residual factors are also correlated. But this is some assumption that you could challenge, you could test. If you have enough degrees of freedom, you can relax that assumption if you want. But typically, this is the way the longitudinal confirmatory factor model is modeled. Oh, yes. Okay, so now let's have a look how we, using this model, how we can test for different levels of longitudinal measurement invariance. Typically 4 different levels. They differ in the stringency with regard to invariance. They are being tested. So the first level of longitudinal measurement invariance that we should test and that we should try out is called the configural invariance model. And that simply means, does the same factor model, the same factor structure, apply for the different time points? So going back to this model, here we assume that all 4 items are reflective of the same single underlying latent variable. So there's one depression construct that all 4 items are indications of. But maybe it could also be that there are 2 dimensions underlying these 4 items. Maybe it's not one unidimensional depression construct, but it is a 2-dimensional depression construct consisting of a cognitive component and a more affective component, for example. It could be the case. And the question now is, for configural invariance, does the same factor model hold across time? So is it indeed the case that there's one underlying factor at time point 1, and it's also one underlying factor at time point 2? It doesn't change from unidimensional to 2-dimensional suddenly, for example. If that would be the case, then the same factor model doesn't apply. It doesn't hold. So configural invariance is already violated, it doesn't hold. So this is the first thing you want to establish, that the same factor model, for example, a one factor model, holds for all time points. Then the second step would already impose some additional constraints to this model. It's called metric invariance. And here we ask ourselves the questions, well, do the factor scores predict the responses on the observed variables equally well across time? In other words, is the strength of the relationship indicated by the factor loadings, is the strength of the relationship connecting the items to the latent variable, is that of the same strength at each time point? So for example, thinking about the guiltiness item, if this is violated, then for example, guiltiness is a very strong indicator of depression at time point 1. But at time point 2, after following the therapy, maybe they have learned that feeling guilty is really not so much associated with depression. And suddenly the strength of that item to depression is really weakened. If that happens, we see different magnitudes of the factor loadings linking the items to the latent variable. And then metric invariance would also be violated. Then the way the items are indicators of depression has shifted. So that's metric invariance. A third step is called scalar invariance, sometimes also called strong invariance. And here we ask ourselves the question, is any difference in response mean the result solely of differences in factor means? We can go back to the equations. We won't do that for now, but then you can see it. I think I have it on the slides later on somewhere. In addition to constraining factor loadings to be equal across the time points, what we already did when we tested for metric invariance, we now also constrain the intercepts. And that, if that holds, this implies that any difference you see in the means on the items are the result of differences on the latent variable level, differences in factor means. Because the strength connecting the item with the factor is the same. The mean can be different, of course, and the intercept is also the same. So in terms of the expected means, any differences in means across the time points can only be the result of differences in factor means. This is what you want, right? Because then we can say, if we see differences on the item level, on the observed level, then we can compare those means, because then we have established that we are really looking at means at the latent level. These differences in means represent true differences in depression scores. It's not a result of measurement bias. It's not a result of a differential strength linking the items with the latent variable. And it's also not related to differences in intercept. So how quickly you are going to answer a yes to this question or a 3 to this guiltiness question. It's unrelated to that, because the intercept would be the same and the factor loadings would be the same. So any differences in item means between time points should then be the result of differences in factor means. We're going to see that later on in the models. And then the most stringent type of invariance is called strict invariance, also called full invariance. And then we ask ourselves the questions, are differences in observed scores across time only due to true differences on the construct and not to any difference in measurement of the construct? So something that we didn't constrain yet in the strong invariance model, but what we are going to constrain in this step is constrain also the residual variances. So the amount of external influence, the amount of measurement error or other influences impacting the answers on this item should also be the same across time points. So this is an additional constraint. And if that holds, then we have full measurement invariance. Then the measurement model is the same in terms of how the model is specified, configural invariance, but then also all the parameters that we estimate in the model are of the same size, the same value between the time points. Then we have reached strict invariance. So to visualize this, the configural invariance model would look like this. We have the same factor model, a one factor model in this case, but it does exactly the same pathways for time point 1 and time point 2, right? We have seen that already. The metric invariance model would impose the first set of constraints, and I highlighted them here. You see now that instead of having stars, and stars stand for we estimate them freely, they can take on any value. Based on the data, we ask R-Lavan to estimate these parameters, and they can turn out differently. The vector loading for variable 2 for time 1 versus time 2. But here we say if metric invariance holds, then the vector loadings, they have the same size. So FL1 connecting variable 2 to vector 1 at time point 1, it should have the same value as that vector loading on time point 2. The same for the vector loadings of item 3 and item 4. Yeah. Is there the mic somewhere?
Because you say all the time, if it holds, does that mean that the model fits?
Yes, I'm going to talk about model fit later on.
I thought
It
so,
indeed means that model fits well.
Okay.
If you impose constraints, the model fit can only get worse.
Okay.
And what you are going to test is whether the deterioration in model fit, so the model fit getting worse, it's non-significant, then you're allowed to make those constraints because it doesn't lead to a worse fit of your model.
Okay.
Going to have a look at that.
Yeah. Good.
But that's the basic idea. The scalar invariance model imposes an additional constraint. We already had the vector loadings being constrained to be equal across time points. Now, in addition, we are also going to constrain the intercepts in our model. So you see IC2, 3, 4, the intercepts of all the items. We are also going to constrain them to be equal. Well, then we see when we look at the equations for the expected means that we already had on one of the previous slides, by doing that, by constraining the intercepts and the vector loadings, we see that between time points, any difference in the mean of variable 2 can only be the result of a difference in vector means between time point 1 and time point 2. It cannot be the result of a difference in intercept or a difference in the vector loadings, the way the strength with which we can connect the item to the latent variable. It can only be a result of true differences in means on the latent level, so the depression score, the true depression scores. That only impacts whether the means on the 2 time points are different by constraining the vector loadings and the intercepts. Yes.
I just have a question, maybe I missed it. Why is the first vector loading a 1 and the other one's like FL2, 3, 4?
This is what I tried to skip for you to not make it too complex, but I knew you were going to ask. That is because you have to kind of scale the latent variable. A latent variable is something that we didn't observe, so it doesn't have a natural scale. If you have an item, you can just compute the mean and the variance. It's in the data, right? But this latent variable is something we define ourselves, so it doesn't have a mean and a variance by definition. So you need to estimate it. And there are 2 ways you need to identify that part of the model. And there are 2 ways of doing that. And I try to prevent that giving you that information, but you want to know, so I'm going to tell you. You can do it in 2 ways. You can either say, well, I'm going to fix the variance of vector 1. So you see it in the star there, down there. I'm going to fix that to 1. That's one option. Then you say, okay, the latent variable, what is most easy to handle? I'm going to say the mean of that latent variable is 0 and the variance is 1. Then I have kind of a standardized standard normal distribution, right, for my latent variable. It's easy. But alternatively, you could also say, no, I'm going to fix the first vector loading or any other vector loading, but typically the first one is chosen. Fix that vector loading to 1. And I'm going to estimate the variance of vector 1. And also I can estimate the vector mean. That is more convenient because if we are going to test differences across time points, you might also at some point be interested in differences between the vector means or vector variances or vector covariances. So at the true level, at the underlying level, the true depression scores, we want to know how does the mean depression scores on time point 1 differ from time point 2 at this latent level, and how are maybe several factors correlated with each other. So that's the reason why in this specification, when testing measurement invariance, it's common to fix the first factor loading to 1, but rather than fixing the variance of the factor to 1. But there are different parameterizations of the same model. In terms of model fits, what we will see later, you will get the same result. And if you standardize all the paths, you will also get the same results. Okay, and then when we look at the strict invariance model, we already had the constraints on the factor loadings and the intercepts. And now, in addition to that, we also say the residual variances of each item are also constrained to be equal across time points. And then we know that differences in observed means across time are only the result of differences in factor means and not any other aspect of the measurement model. And in addition to that, differences in observed covariances across time, variances or covariances, are also only the result of differences in factor variances or covariances. So in terms of measurement model, how we link what we have observed to what is latent, everything is the same across time points. So everything we see as different at the observed level should be the result then of something being different at the latent level, which we say is the true level. So then we have reached full longitudinal measurement invariance, strict invariance, longitudinal measurement invariance. Model fits, of course, how we're going to evaluate these models. Well, you can look at the fit of each model. Does the model fit well to the data? Using standard model fit indices, and there are still also a lot of debates about which ones you should use and which cutoff values you should use. This holds for statistical equation modeling in general, but also more specifically to measurement invariance models. So typically you look at things like the chi-square test, which we know is influenced by sample size and also model complexity, by the way. The root mean square of error approximation, the CFI and the TLI, 2 other fit indices, are typically chosen, but there are others out there, and there are also variations on these, like the robust CFI. We will see it in the output later on. And it's really difficult to say which ones are the best, but these are typically being used. And when it comes down to model comparisons, we want to know whether the constraints that we impose on the models in these different steps, whether they don't lead to a worse fit, whether the factor loadings, for example, can be constrained to be equal. Then they should not be too different, because that will lead to really worsening of the fits. Then you're not allowed to constrain them, right? So for that, you can look at difference values of these fit indices, like the difference in chi-square, the chi-square difference test, or the difference in the RMSEA value, or CFI, for example. And here on the slide, I've put 3 references that are nowadays quite commonly used. They sometimes differ in the cutoffs they propose. So these are this is kind of a summary of this, a rough summary, where they say, well, the RMSEA should not change by more than 0.03 points, and the CFI not more than 0.01 points. But there's still a lot of debate about this. Okay. Another thing you should know about is the difference between having continuous and categorical indicators. You might have been thinking about this with the guiltiness item already. For categories, this is categorical, right? Many of the items we study in questionnaires consist of a limited number of answer options, like 3 answer options, maybe 4, 5, 7 is already quite a lot. You could say, well, we could treat that as continuous if it's like 7, but if it's less, that's definitely a problem. And some categories might also not be answered very frequently. So we might have empty cells and stuff like that. So typically, if you can treat your indicators, so your observed variables, as continuous, then you are dealing with those 4 levels of measurement invariance, like we discussed. But if you have categorical indicators, there's an alternative model that you might need to use, which is called the threshold model. And then you can only test for 3 levels of measurement invariance. Basically, That's because what we say is, well, we already linked the guiltiness item to the latent variable, depression, right? But since guiltiness is actually a categorical item consisting of 4 answer options, you should say, well, we should put something in between. In fact, people can only answer 0, 1, 2, or 3, right? Feeling not guilty or all the time guilty. Those are the 4 options that people are given. But you could think of a latent variable underlying that item that represents some kind of continuous scale of how guilty people feel. And you could, that is the threshold model. You could say, well, there's also this normal distribution, this continuous distribution for guiltiness. And as soon as people score very high above a certain threshold on this latent guiltiness variable, then they will cross the 3 if they are beyond that threshold. If they are below that threshold and they are just a bit lower, they might cross a 2 or a 1 or a 0. And the same applies, like you asked with the, I think you asked about the scaling of the factor. Here we also have another latent variable for guiltiness, and we have the same problem. We should give it a scale because the scale is arbitrary. So typically what we say, well, we assume a standard normal distribution for that latent variable. We say it has a mean of 0 and a variance of 1. But that implies that we cannot, the variance is fixed already. So we cannot at the same time estimate, well, intercepts or thresholds in this case. It becomes a bit complex, and the variances at the same time. So testing both intercepts and residual variances in 2 separate steps is no longer possible. That's kind of the take-home message. So when you're dealing with categorical indicators, you might want to run a threshold model, and you can only test for 3 different levels, depending on the parameterization, it is called, of your model. Just as a side note, so you are aware of this, you might encounter it in articles and also in practice when you are going to test for measurement invariance yourself. Annalena.
And can you do this also with dichotomous variables?
Yes, you can also do this with dichotomous variables. So then you would only have 1 threshold. You see here 3 blue lines, and it kind of separates the latent distribution into 4 categories. Mm-hmm. So once you pass the first threshold, you will answer 1 on this questionnaire. If you pass the second threshold, you will answer 2. If you pass the third threshold, you will answer 3. So with 4 answer categories, you have 3 thresholds to be estimated if you fix the scale of the latent variable. If you have a dichotomous variable, you will only have 1 threshold.
Yeah, okay.
But you still need to fix the distribution, like saying it's standard normal, for example. Okay, let's have a look at an application. It's time for that. This is something we also worked on within the Generation Squared study, not the Growing Up in Ireland study, but in collaboration with deMoor. And this was about parenting self-efficacy. So the perceived ability, perceived competence of a parent with regards to its parenting role. It's almost to be submitted. The goal was that it was submitted before I was here, but we didn't manage, but we are in a far stage with this paper. And we really wanted to know, well, this observed increase in parenting self-efficacy that we see in the data, is this true? Is this a true change, or is there also some measurement bias? Because you can imagine that when